Let us now discuss the strain components in cylindrical coordinates. So we try to examine the strain within this element 1, 2, 3, 4, which is cut out from our cylindrical body, which is shown over here. So this by cylindrical coordinates, we mean that we are gonna consider this body within r, theta, and z coordinate system. In considering the displacements in the cylindrical coordinate system, let us assume that u is a component of displacement in the radial direction and v is the component of displacement in the tangential direction. So this element would have a displacement component in the r direction denoted by u and in the tangential direction denoted by v. We have four sides of this element. 1 and 3 are the two surfaces and 2 and 4 are the two sections. 1 and 3 have got outward drawn normal in the radial direction, whereas 2 and 4 have got the outward drawn normal in the tangential direction. This element is drawn in x1, x2 coordinate system, which have got origin at point O, and O is considered fixed. This element is located at an angle theta from OX1 axis, and AD, or the surface 3, is at a distance r from the origin O. Similarly, BC, or surface 1, is at a distance r plus dr from the origin O. In other words, in order to draw AD or BC, which are the sectors of a circle, we will need radius r and radius r plus dr respectively. Now let us remind ourselves of the strain at a point, which we define as change in length by original length if our element becomes very small. So this is something which we defined while deriving our strains in the Cartesian coordinate system. So we had an element AB within the body, and that was deformed into A dash B dash. We said that if we make the L dash length of A dash B dash subtracted from the original length L of AB and then divided by the original length and make B approach A, in other words, make this element very small, we will get a strain at a point that is called a normal strain at A along the vector n being in the direction of AB. The same approach can be followed in the case of strain components in the cylindrical coordinates. So in the case of radial strain, we have the change in length, which is u plus change in u with respect to r times dr. So AD, so the displacement component of AD is considered as u, and as we move along the r towards surface 1, we experience a change in u with respect to r. So imagine if we have got a bar of length L and we are pulling that bar, we are saying that as we move along the bar, there is a change in displacement because of the strain developing in the bar. So similar idea can be applied over here. As we move from surface 3 to surface 1, we have a change in displacement appearing. So that total displacement is u, the displacement of surface 3, plus rate of change of u with respect to r. So this is the ratio, and multiply that with dr, we get the total displacement between surface 1 and 3. We subtract that from the displacement of 3, which is u, and we get the change in length. We divide that by the radius dr, and hence we will get partial u by partial r. Mean to say that u will get cancelled with this u, and then dr will get cancelled with the dr in the denominator. In the end, we will be left with the partial u by partial r. This is similar to what we got in the case of Cartesian coordinate system. We had the strain in one direction equal to partial u1 by partial x1. So there is an analogy between the normal strain in Cartesian coordinate system and the radial strain in the cylindrical coordinate system. So this is our first strain expression. The second expression will be corresponding to the tangential direction. In order to determine the tangential strain, we have to bring the concept of a rigid body into our system. A rigid body is a body which displaces from one point to another without any imposition of strains. So it is just like picking a body from one place and just placing it in another place without inducing any strain. Over here, a question might arise that why do we have to introduce the concept of rigid body within the system? The answer has got to do with the stiffness in the in-plane direction of our cylindrical body. Our cylindrical body has got a dimension z in the z direction. It has got some material in the r direction, and then it has got an area in r theta direction. After deformation, the elements which are in this region, which is the r theta region, they can displace easily. So if we assume that we have got a circular plate whose thickness is in x3 direction or in the z direction, and the elements have got a tendency to deform more in the theta direction as compared to the deformation in r direction or in the z direction. Because there is more material in the r direction and there is more material in the z direction, these deformations will not include any rigid body movement. However, along the tangential direction or theta direction, there is a tendency of this body to deform a lot. As a result, there can be some rigid body movements also included when the body deforms in the tangential direction. Looking at this picture, what we are saying is that in the r direction, this element can deform, but there won't be any rigid body movement. And we assume that it is because that it is the stiffness of the body along the r direction is higher. Similarly, in the case of z direction, again, there is less chance of any rigid body movement. However, in the case of the tangential direction, there is a chance of this body to have some rigid body movements. If in a body we have rigid body movements, we have to subtract that from the overall displacement in order to get those displacements which will induce strains. Please remember, strains are not induced by rigid body displacements. So we imagine this body which is lying at a surface. If this body is lifted and placed at another surface, that doesn't introduce any strain in the body. But if the same body is stretched, then that will induce strain in the body. So we have this body, we have got this element in the strain R direction, and after deformation, we will have some stretching. That means that there is no rigid body movement in the squishing or stretching of this body along the R direction. Please note that this body is getting stretched and squished in the R direction. Similarly, if we assume that along the Z direction, if we have got an element, this element, if we move along the Z direction, it is getting stretched and squished. But there is no rigid body movement in this body or element. So along the tangential direction, a body will slightly move in a rigid body fashion, and then in addition to that, there will be a stretching or a squishing. Therefore, we will have to subtract the rigid body movement from the overall displacement of this element. That is one thing, that we have rigid body displacements in the case of tangential strains. The other thing is that because of this rigid body displacement, we have this element changing its shape in both radial and the tangential direction. So when this element was part of strain R or in the radial direction, there is a displacement of this element only in the radial direction without disturbing or without causing any displacement in the tangential direction. Another element which is having displacement along Z direction will have displacement only in the Z direction without any displacement in the tangential or the radial direction. However, in case of in-plane element which is getting displaced in the tangential direction, that will have some displacement in the radial direction also. So we have discussed two important points related to tangential strain. One is that there are rigid body displacements in the element A, B, C, D when that is getting displaced in the tangential direction. Secondly, the displacement in the tangential direction will also cause a displacement along the radial direction of this element, thus reiterating that the strain in the tangential direction depend not only on the displacement V, bearing in mind V is the displacement in the tangential direction, but also on the radial displacement U. We assume that the points A and D of the element A, B, C, D have only the radial displacement U. The new length of the arc would then be R plus U d theta. So we have this AD and that has moved to AD prime. We have a new length of this arc which is R plus U d theta, and we subtract it from the original length which is AD, and that is R d theta, and we divide it by the original length which is R d theta. That gives us the term U by R. This is the radial strain component in the overall tangential strain of the element. The other sides or the other sections of the element, i.e. AB and CD displacement, will now be considered. We assume that our element ABCD has moved to the new position shown by this red element. So DC has moved by distance V and AB has moved by V plus rate of change of V with respect to theta multiplied by theta. Since V is changing along the theta, therefore in the rate we have taken the change with respect to theta. Please note, d theta is actually the internal angle of this sector. Thus we subtract the displacement v plus rate of change of displacement v with respect to theta times d theta minus v, and divide that by the original length, which is r d theta. The reason why we are dividing this whole expression by r d theta can be explained by considering this green line element shown in the figure. So imagine this green line element was on the top of AD before application of the load. Now it has moved to its new position shown within the red box. So initially its length was r d theta, and now in the current location its displacement is v plus rate of change of v with respect to theta times d theta minus v. So that gives us the change in length by original length. Adding these two expressions will give us the total tangential strain within the element. So in the case of tangential strain, we have added the contribution of the radial displacement and the tangential displacement of the element. The rigid body motion will be subtracted when we are trying to derive the shear strain, which is gamma r theta. The effect of rigid body is included in the shear strain, and that will be discussed now. So again, we have got an element, the same element A, B, C, D. And we assume that after deformation, the new position of the element is shown by A dash, B dash, C dash, D dash. We remind ourselves that the shear strain of an element in Cartesian coordinate system is equal to the rotation of the element with respect to the two coordinate system. So our gamma was equal to rate of change of displacement in the x2 direction plus rate of change of displacement in the x1 direction. In other words, the shear strain of an element was taken as the summation of the rotation of the two concurrent sides corresponding to the axis of the coordinate. The same idea can be employed in working out the shear strain gamma r theta. This is, we are talking about the element in the r theta plane. So we have the angle of the angle between AD and A prime D prime, and the angle between AB and A prime B prime. Since we have called the displacement in the radial direction as u, we can say that this angle is partial u by r d theta, and that has been written over here, partial u by r partial theta, and that is the same thing which we did previously. Our angle was equal to u2 by x1, which is given over here, and similarly this side was equal to u1 by x2, which is given over here. In limit, it will turn into partial u2 by partial x1 and partial u1 by partial x2. The shear strain is equal to summation of these two angles. In the case of AB, as we discussed previously, we will have the total rotation which will involve rigid body rotation also. So in the tangential direction, we have partial V by partial R, remembering that AB is equal to dr or partial r. So partial V by partial r will include the rigid body rotation, and that rigid body rotation will have to be subtracted from the overall angle. Therefore, the displacement V by r has been subtracted from partial V by partial r. So just to emphasize the importance of rigid body movement within the plane of our body, we assume the axial strain of the element in the tangential direction will include the effect of radial displacement and the tangential displacement. And in shear strain, it will include the effect of the rigid body rotation. The magnitude of the rigid body rotation is taken as V by R, which represents the angular displacement due to rotation of the element ABCD as a rigid body about the axis through O. After gamma R theta, we have shear strain gamma theta Z, which is relatively straightforward. So we have theta Z axis in this 3D figure. We have theta Z axis and the element is within this theta Z plane. The element length along the Z is dz and the element length along theta is rd theta. In other words, we have got the same element whose one side is AD and another side is along the out of plane Z direction. As we said that the displacement in the theta direction is V and we assume that the displacement in Z direction is uz. So in order to find out this angle, we can say this is partial V by partial Z, which is the second term of this expression. And the other angle is partial uz by r partial theta. Thus, that will give us the shear strain gamma theta Z. Similarly, in order to find out the shear strain gamma rz, we will consider our element in the rz plane. So imagine we have this rz plane and we consider an element which is dr along r-axis and dz along the z-axis. Again, after deformation, we would have this element converting into a parallelogram. So we have to find out these two angles and sum them up to get the shear strain. So this is relatively straightforward if we assume that the displacement in the z direction is partial uz. So the angle contributed by uz is partial uz by partial r. And the angle due to the displacement u along r will be partial u by partial z.